All right, so here, the formula we have on the board, it is kind of new. Can you put a little line underneath P, V, N, and T? P, V, N, and T. We recognize that those are the four main variables of gases that we deal with, yeah? In fact, last class period, we had you guys act out the relationships between those. This equation ties in all four of those variables to each other. And this is it's known as the ideal gas law. We also view it as a snapshot in time, because here's why. What we can do in a problem is we can give you three out of those five variables, and you can solve for the fifth. Now, the reason I say three out of those five is, see that R right there? Isn't that a gas constant, which never changes? And because you have memorized it, at least I hope some of you guys did, and hopefully that wasn't the mistakes you made on the quiz, is that number is always given to you, or you have it in your head. Agree? So if we know that what R is all the time, given three of the other four variables, can't we always solve for the fourth? In fact, I think it would be insulting to your intelligence if I were to do problems like this and just have you do, hey, here's three variables, solve for a fourth. Here's three variables, solve for a fourth. You guys would get really tired really quickly and go, come on, man. We've been doing this since 7th grade. Agree? Now, what makes these problems unique is the gas constant, R. So can you write R over here? And you guys memorized it, hopefully, for the quiz today. But isn't the gas constant 0.08206? You'll see it often rounded up to 0.0821, but we're going to keep it as 0.08206. And then the units are liters times atmospheres on the top. So we go liters dot atmospheres. And on the bottom, moles dot Kelvin. Okay, and let's just go to the OS on the end of atmosphere, because the abbreviation for atmosphere is ATM. And that's actually the unit that we're dealing with as well. So what actually makes this a little bit challenging is that often in problems, and by often I mean always in problems, they're going to give you units that don't match up perfectly with the units in the gas constant. Because we have that constant in the problem, it has specific units, it means that all of the variables that are underlined, see the P, V, N, and T, all of them must be in the units that are given in the gas constant. Are you with me? As you already know, it is very unlikely, because that's how evil we are, that we're ever going to give you all four of those units, liters, atmospheres, moles, and Kelvin. We will give you things instead like milliliters instead of liters. And instead of Kelvin, we'll give you Celsius. Instead of moles, we'll give you grams or molecules. It is root. And instead of temperature in Kelvin, we'll give you temperature in Celsius. Now, be careful with this. One of the things that I've noticed students do a lot of is we just start plugging numbers into an equation before we've rearranged the equation. So what I really encourage you when we do all the problems that we're going to do today is I encourage you to go isolate or look at, this is what we're solving. Like literally like, aha, put your finger on whatever we're solving, and then rearrange the variables, and then just plug and chug. Plug the numbers in and cancel out the units. Now, the other thing I would say, this is an old school expression that you're looking at me weird with, plug and chug is plug the numbers in and chug on through. The other thing we want to worry about here is the conversions. So I would suggest doing the conversions on the left-hand side of your problem before you start even doing anything with the problem. So let's write on the left-hand side. I'm going to just give you a random problem. You might want to move the laptop, maybe put it on top of the podium, or yeah. So here's the actual problem. I would like you all to read. I'm doing this off the top of my head. So this is the problem I want you to solve. All right. Given. So let's write as high up as you can, and let's try and write. Are you writing in blue or black?
I'm writing in black.
Perfect. Given 920 torr, 920.0 torr. Let's just erase it. Erase it. We'll start again. Okay. Given a pressure of it's the same thing, but if you ever see they might just give you a bunch of numbers and not tell you what the variables of. So do you realize if I give you torr, isn't that pressure? So I'm gonna assume that you understand what the units are for, but in this case here, given a pressure of 900 and what the number did I give you? 920.0 torr. And in a 500.0 milliliter container, at a temperature of 20.0 degrees Celsius, what are the number of moles?
What are the number of moles?
What are the number of moles? Okay, so I can't really read what you're writing, but I'm assuming you just wrote what I said. Yes. All right. How many guys here, just a show of hands, love problem solving? Like problem solving, and you are best friends. Hands up, like literally, like it's your favorite. How many of you guys are okay with it, but not your favorite? How many of you like have a deep-seated hatred of problem solving? Okay, and one of the problems that we have, and one of the reasons that we have that deep-seated hatred in general, is we don't know where to go. Isn't that the number one problem with problem solving? Is like, what are we trying to solve for, or where are we trying to go? So whenever we approach problem solving here in chemistry, what we're going to do is this: we're always going to identify what are they asking for, and in this case, what are they asking for? Moles, right? Or N, as Hayden said. So what I want you to do literally is this: go to the problem, go to the equation, put your finger on the moles. That would be N. Agree? Now make sure you're going to stop blocking the camera. It's like it's, actually, you can bring I suggest bringing it towards the middle here. So whatever you're doing, just make sure that they can see what's being done before. So if you put your finger on N, can we rearrange to get N by itself? And here's what I want you to do. I want you to put the variables surrounding that without putting any numbers in it. Would you agree with me that RT has to be gotten rid of? Divide by RT on both sides, right? So can we write on the left-hand side of that, can we just write the rearranged version, which would be PV over RT equals N. Okay, so is everyone okay with that? Is the rearranged form of Pivnert. I'm going to call that Pivnert out of just love and care for because I've used it so often, but Pivnert is that formula. Now, in order to solve now, we just have to make sure that we have all the variables in the units that match the gas constant. So if you take a look at the gas constant, mustn't we have liters, atmospheres, moles, and Kelvin? Yeah. So let's start with the first piece of information they give us. What is that? Now, I was gentle in this problem because didn't I tell you that that's the unit for pressure? Sometimes they won't do that, so we just have to recognize what the unit for pressure is. So in this case right here, what is our pressure they give us? 900 torr. So what I would suggest doing is always do this down the left-hand margin of where your problem is. Just do a little conversion space. So let's start with 920.0 torr, I believe it is, right? And what do we have to convert torr to?
ATM.
ATM. Now watch. Let me point this out to you right now. See these units right here? I'm doing this literally for you right now, and you're not looking at me. Watch. Liters, atmospheres, moles, and Kelvin. Those are the units that these things have to be in. Now, if they give us units other than that, our job is to convert. Now, at the top of the second page, isn't there a conversion table for all of this? This is one of the homework quizzes you have to do for not being that you didn't take today. Same thing for you. We gave you the quiz on the chart. Doesn't it say 760 torr is equal to 1 atmosphere?
Yes.
And just like every other conversion we have, now that's a tool. So I would suggest doing this. If we start off with 920.0 torr, let's do our little table of death. And can we put the torr and the atmospheres in such a way that torr will cancel out and atmospheres will be left? And how would we do that? Yeah, can we put 760 torr on the bottom? Incidentally, the conversions that are on the table, those are exact numbers, so we don't have to worry about the significant figures.
Always divide.
And 1 atmosphere on the top. Now, if you're like going, well, how do I know to do this? Well, if you take a look at the gas constant, and incidentally, after you do a few problems on this, you're going to realize your problems need to be in atmospheres. So in this case right here, wouldn't it just be dividing those two numbers together? I'm desperately hoping that you all have your calculators, so please pull those out. And I would like you all to kind of be doing this along with. So all you have to do is divide 920 by 760. Won't that give us the number of atmospheres we have? Say again, please.
1.21.
1.211. And I don't mind right now, and you write ATM because that's kind of a big deal. And can we cancel out? So go back to the formula. You see what she just did, the way she set it up? Doesn't torr cancel?
Okay.
Everyone see that? Now, I know that some of you are looking at it and going, wait, but weren't there 4 significant figures, so we do 4 significant figures here? True. But I would suggest this. Whenever we're dealing with significant figures, keep as many significant figures throughout the entire problem, and only when they ask you for a result, when they ask you for an answer, that's when we do the change back to the correct significant figures. In this case right here, right, and by the way, I would do this. Can you write P equals, and then on the left-hand side? Well, no, right next to where you actually did the pressure. I feel like someone put the sign right on my board. Let's put that on the window. I'm guessing it was maybe. No. Okay, can you write P equals? So what I kind of want to do is I want to go through all the variables that they give us. So what's the next variable they give us in the problem?
Milliliters. So.
Milliliters, right? Isn't milliliters a unit of what? Oh gosh, yes. It's a unit of volume. Can you write V equals?
Underneath.
Yeah. What we want to do is we want to write all the variables that we have in the correct unit so we can plug them into our problem. Yeah. So our V in this case needs to be in what unit? Based on the gas constant. Doesn't it have to be in liters?
Yes.
So let's start off with our milliliters. And again, table of deficit. And here's where you can do one of 2 ways. It depends on how comfortable you are with units. Was it 1 milli of anything, 10 to the negative third of that thing? So wouldn't 1 milliliter be 10 to the negative 3 liters? Or, because we're going to do this so often, are you aware that 1 liter is equal to 1,000 milliliters? I suggest feeling really comfortable with that unit. And I would just go 1,000 milliliters on the bottom and 1 liter on the top. Are you guys okay with that? We could absolutely do this. We can write 1 milliliter is equal to 10 to the negative 3 liters. But the only problem then is we're going to deal with exponents, which is fine. But yeah, this is the problem. And incidentally, whenever you're dividing by 1,000 and you're in the 100 spot, isn't just like shifting the place over 3 places. So that's going to give us equal. Good job. Canceling is going to equal 0.5000. Oh, no. Well, we're in fairness to you, we're kind of new at this, right? So now we have the volume. What are the information they give us? Let's keep on reading. They give us a temperature of 20 degrees Celsius. So why don't we put the T maybe on top because we have a little more space there. Well, on top where the P is, just we aren't going to need that much space. So temperature, and in this case, don't they give us Celsius to begin with?
No.
Yeah, they gave us Celsius.
So let's write the Celsius temperature, fully knowing that that Celsius temperature, I just realized my voice probably picked up on the mic very well. Fully knowing that that Celsius temperature has to go, right? I think I said 20.0, but can you make that 20.0? Because if not, we'll only have 2 significant figures in our problem. So, how do we get between Celsius and what is the unit we need to do every single gas problem in terms of pressure, or in terms of temperature? Kelvin. Listen carefully on this. There is no time in this entire unit when you plug a temperature into a problem that it stays as Celsius or Fahrenheit. Every single time it has to be converted to Kelvin. Can I get a head ball on that? And that avoids us the unfortunateness of potentially having a zero as part of our mathematics, which would then invalidate our whole equation. Does that kind of make sense? Absolute zero is the only time you have zero, and you're never going to have a problem when we're dealing with absolute zero in one of these problems. So if we have 20.0 degrees Celsius, can we just write degree and then this capital C? We don't have to write all Celsius in there, although that is very thorough. And let's just go this. Isn't it plus 273.15? Get the Kelvin. So let's go plus 273.15. And that will give you equals Kelvin. So we're going to have on the bottom of that, or somewhere near that, wherever you want to write, 293.15.
You're just going to add that.
Yeah, that literally is how we get to Kelvin every single time. 293.15. And that's K for Kelvin. Incidentally, you're going to get varying degrees of lazy in problems sometimes, and even in answers, where they don't go 273.15, they go 273.2 or 273 point nothing, or just 273. So right now, don't we have the temperature, the pressure, and the volume? I like to do this in my problems. Can you write N equals and a question mark at the very top? Oh, no, I mean like still part of our problem, but right here. N equals and a question mark. I like to be able to associate what we actually need for the problem at the very top, agree? What is the variable we're solving for? Let's keep that at the top. Now the only variable we're missing, isn't it R? Now, we do, and here's the thing. You can write down your R in every single problem so you have it there handy, and that may help you remember that this is what R is. But as long as you in your mind know that the R is a given, then I don't see any necessity to write it again right here if you know what it is. Does that make sense? I mean, in reality, yes. What we have is this right here should be written here as part of all your variables. Now, if you have R, V, P, and T, aren't they all of the variables that are right over here that we're trying to solve for? And won't that give us N if we needed it? So let's set it up. Let's write right in here in this space right here. Let's actually write the variables in. So literally what we're doing, it's kind of hard to see right now. We rearrange the equation. This is the golden equation right here. Agree? So now all we have to do is we can take the units that we've converted correctly and just plug them into these spaces. So now is where we can hammer in the numbers. So let's do that right next to us, starting with the pressure.
You want us to write these as well? Okay, just want to make sure.
Our final unit is going to be more.
We hope. And here's what's cool about this. And by cool, I mean moderately interesting. If you do these, this really is not that cool. I was going to try and sell it, but I can't. What is kind of neat about this, neat's probably a more geekish way of saying this. What's neat about this is if you do your conversions right and you do your rearrangement right of your equation, the only unit that's left standing is going to be moles, and that's a way to check your work to make sure that you knew the problem correctly. So when we get done, and we're going to go in a little canceling frenzy in a minute. When we have all of the variables, we're going to cancel them all out. The only unit that should be left standing is moles, or we've done something wrong. Right, there is no moles, which means that the constant that has moles, this right here, that should be the only unit that's not canceled out.
Oh, that's
It's 0.8.
Oh,
0.0826. Now, I'm going to jump in here because I'm a canceling expert. Let's just go through the units here and let's talk about where they are. Do we have atmospheres on the top and atmospheres right underneath it being divided?
Yes.
So when these atmospheres cancel? Yes, teacher. Great. How about liters right here? Don't we also have liters right underneath it? Great. Now, also, this is like a separate world, isn't it? Don't we have Kelvin here? And then if you did the number, if you actually look this up, isn't this really all over 1?
Yes.
You do understand that, right? If I just have a number. So if I look at these two right here, isn't there a Kelvin on the top and Kelvin on the bottom right here? Right? What's the only unit that's left standing? Moles. Now, some of you may be like, wait, moles on the bottom. No, it's not. Because isn't it this divided by this over this? You guys realize if ever you have a number and you have 1 over x, do you realize whenever you're dividing, so you're dividing by a fraction, can't you multiply by the reciprocal? So that is equal to x. Just like this over this unit-wise over mole. So right, we have unit-wise, we have this. Because we have no units other than mole. Wouldn't that be the same as mole? Now, I'm only sharing this with you here because sometimes we have difficulty manipulating equations. But getting back to what Hayden was bringing up, the only unit that should be left in our problem is moles. Now, that being the case, all we have to do is multiply these two on the top. And please, for the love of all that is good and noble and pure, this times this, divided by this, divided by this. Do not punch this in. This times this, divided by this, times this, because that's the same as bringing that onto the top. If you want to parenthesize, absolutely. And most of you guys have your TI 90 billion, whatever, and it's like, hello, and you speak to it, and it's like, I will do this for you. And if you decide you want to go parentheses here and divide between them, have at. So someone who's already done this, can you guys please tell what the number is, and maybe I can get individual corroboration. And when I say if someone who's done this, I want all of your calculators out, because I think I threatened something if you didn't bring your calculators.
What do you want me to write? N equals or more?
N equals.
It's 0.025161.
0 point, say again?
0.025161.
I need to get independent verification of that. You got one? You got 171? All right, one more person here. Let's get an independent verification of this.
Megan, can you use the full 1.21053?
I just two. I got 0.0251.
Yeah, then mine should be
71.
You got 0 point, say again?
0.025171.
So there's a 7 there. I've heard 2 7s on that. Can I get
He used
a?
more exact number.
Okay, so and this is where I'm going to be okay with this. Okay, I don't want to hear that. But thank you again for throwing out a wrench in that whole thing. I would suggest. Did you do a lesson? Where did you round?
When we did P, it's actually 1.21053.
Okay.
I used like a 12 digit.
Yeah. So watch. Y'all with me here? This is delightful because what happened right here between what Kaden did and I believe who's the person that back did this? At Catherine and Megan. You guys right here use the numbers we did right here where we at the pressure we did 1.211, right? So we made a choice to round off at 4 significant figures. But you can carry all the significant figures. So your number was like 1. What did you say it was? 1.2105 something.
0.0251.
I used 1.210.
I got 0.0255.
Yeah, so watch.
That's horrible.
If you take a look at the number here, just put your finger on the 6 where the number was different. So right now, 0.02516, he had 0.02517.
No, this is
Oh, 6,
his.
and
I
then
wrote
and
out his.
then you guys had 7.
Yeah, I
So
wrote out his.
you do realize that we're talking about the 10,000th place, right?
Well, that's a big number.
Yeah, that's a lot of parts.
That would be a decent number of progress.
No matter what,
What?
we still, when we go for, still have
With both of these answers.
Now watch. We're allowed to have how many significant figures?
This doesn't matter.
four.
We're allowed to have 4, right? So wouldn't the first 2 significant figures, 2 zeros, not matter? Right? So then our number would end up, if we cut it off, it would have to be 251 and then cut off at that right there. That's our answer. Remember, leading zeros are never significant.
Wait, so
I feel like it's.
where do we get our significant figures from? From which
The lowest, the least number you do the math by in the entire problem.
in the front, like the given?
In the givens, not the conversions, in the givens.
Because these are constants.
Wait.
Yes, sir.
That'd be fine.
Well, if only if you decide you want to make it into scientific notation, you can slide it over and go 2.516 times 10 to the negative
Did you
2.
just say the least?
Yeah, we should always.
Oh, so stop. Hold on. Now, this is important. So a number of you guys said, well, everyone watch. We want to use the least number of significant figures in what we're multiplying. Agree? Agree? So when we're doing this, and we have, you guys mentioned Celsius. Isn't Celsius 20.0 degrees Celsius? Right? When we add, remember, adding significant figures is different than multiplying. When we add 273.15, right? Wouldn't that become then what? 293.15. Wouldn't the line of death go right here? So in reality, we should have, if we were cutting it off here, it would be 293.2, which would still be 4 significant figures. Now, we kept this whole number in here because the rule, and this is a weird rule. The weird rule is the best time to do your significant figure rounding is the very last step, which is what you did. But it's equally okay to round it into each individual step as well. So both answers would be right, but here's how, this is the reason we got 4 significant figures instead of 3 from the 20.0. Now, David, if we've been multiplying, if we had this 20.0 and it was actually part of this right here, I guess you can, and this 500, by the way, isn't it 5.5000? Yes, ma'am. The least number of significant figures in the problem when you're multiplying. So whatever's the least that you used.
We didn't have a 4-0 here, I guess.
Right here.
No, I know we have a 4-0 there, but when
It should have been one more
zoomed
here.
out,
0.5000. Yeah, I didn't notice that happen. Okay, now watch. I want to point something out to you here. What if I'd said in this problem, given a pressure, blah, 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 how many moles of oxygen, O2? Can you write, instead in the question mark, where Sarah says of moles up in the actual problem, Sarah says question mark. Instead of saying of moles, let's say, so that's part 1. Okay, let's do part B so we don't have to change it. So that's part B. How many grams of oxygen? How many grams of oxygen? I'm going to show you what I mean. I'll show you what I'm going to do right here. So let's say instead of, you guys see where it says how many moles are there in the original problem? Let's say instead of how many moles, the question said how many grams of O2. Let's say that was the problem. Now, watch. In our overall equation, in our Pivnert equation, is there any place for grams?
No.
No. What's the closest thing we have to grams? Moles. So now watch. We didn't do it here, but if they asked us to solve for grams, wouldn't that be the same as asking you to solve first for moles and then convert from moles to grams? So let's just say this problem had been written, and the problem said, blah, 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 blah. How many grams of O2? Oh, by the way, instead of saying how many grams of O2, couldn't I be okay with saying what is the mass of O2? Wouldn't that work as well? I can, because I'm the boss of me, right? Now, if I look at this right here, and this is where you guys have to focus in on what is the problem asking. If the problem says how many grams of O2, we look at our equation and we go, there are no place here for grams.
Right.
But we could solve for moles, couldn't we? And then once we have moles, can't we use the molar mass of O2 to get to grams?
Right.
So anytime, and this is just a reminder and or a hint, anytime they ask you to solve for mass, you must solve for moles in the Pivnert problem. Do y'all hear me? Or vice versa. If they ever give you grams in a problem, you can't plug grams into this. But just like we did the conversion, now in this problem, we were solving for n, but if they gave us grams, wouldn't our step in solving for moles be convert from grams to moles? A little bit? Any questions here? Now, here's what I want to do. And I was going to teach you. So let me backtrack. Anytime you see a problem, and the problem's this, ready? Here's a piece of information about a gas, solve. It's like, here's the pressure, here's the volume, blah, blah, blah. Any of those 4 variables, if they give you any of those 4, let me phrase this way. If they give you 3 of those 4 variables, you're always going to use this equation to solve. Now, there's a separate type of problem where they change some of the variables of a gas, and we're going to use something called the combined gas law. But I want to make sure we feel really comfortable with working through problems like this. I know I only gave you 1 problem. So can you grab the worksheets on the far left?
All 3.
Just the far left. I want to show people on the screen real quick. So this worksheet right here, it actually, as a gift, gives you the formula that we're going to be using throughout the problem. And all the way through this, there are problems that have you rearranging the equations to solve. I can't think of no better way to feel comfortable with this than start practicing on these. So this is going to be your homework. This right here, whatever you don't get done in class. I'm going to see how, can you do me, like, honestly do me a favor. I'm going to take the next, like, 15 minutes, 10 to till about 20 till. And I want you to tell me at the end of 15 minutes whether or not this has gotten to the point where it becomes repetitive for you. You follow what I'm saying? Like, okay, I get it already. If not, we'll do a little bit more. If it has become repetitive and you feel really comfortable with it, I want to teach you one more thing. Is that cool? Okay, so that's all we have for the broadcast. I want everyone right now